Hey everyone, my name is Brian Singh. Today I will present my project titled Comparison between VectorRAG and GraphRAG Architecture for Personal Driven Voice Agent. This project investigates how the RAG architectures affect the real-time AI voice agent. Okay, now let's do for the assignment. What is the capital of Australia?
The capital of Australia is Sydney.
Sydney? I thought it's Canberra. Let me ask LM. What is the capital of Australia?
The capital of Australia is Canberra. It's a planned city specifically built to serve as the national capital, and it's located in the Australian Capital Territory.
Why these two LM give different answers? Let me research for it. RAG is introduced. Oh, so the modern LM using the RAG architecture, it connects the external database to the LM, and the user is asking the questions. You search from the database first, then retrieve the most relevant context and use context to the LM to help the LM generate the trueness and newest answers. So that's why the modern LM can answer it correctly. However, the previous research only focused on text-based only. So for the paper research, I found that GraphRAG answer the questions take more time than VectorRAG. So why don't I develop a voice agent and compare both VectorRAG and GraphRAG and see whether the GraphRAG can answer more questions accurately, but with lesser latency, they cannot be noticed by users. So the previous research mainly focused on text-based, they still lack of abbreviation on the voice-based. So this is the difference in the diagram. You can see that when the users have to undergo RCT, then retrieval the requirement information passed to LM to generate the answers. They have to return a response and to the TTS and synthesize the audio. However, the difference between text-based, which is the latency, is crucial in conversation, and also the user theory is not perfect. So first of all, what is RAG? When user asks about who invented Tesla, so VectorRAG first, embedding the query first, then it will undergo similar search and retrieval the top 5 chunks that have top similarity to the particular questions to the LM. Then for the GraphRAG will extract the entity first, then look up the nodes in the knowledge graph, and then we will perform cross traversal to get the relevant context. So the embeddings is used to convert the words that have similar meanings that to have same vectors. When the users ask, it will search the context that have the embeddings that similar to the query questions, and he will pick the most 5 chunks that have top similarity and pass the relevant context to the LM. But for the GraphRAG, he will search for the nodes and it will perform the cross traversal, which is you can see the Tesla, then get invented by Tesla company, then owned by Elon Musk, and he will get the facts of these nodes and pass it back to the LM.
What special cells in the eyes communicate directly to the SCN cells?
The retina of the eye contains specialized ganglion cells that are directly photosensitive and project directly to the SCN.
The ancestors of the modern-day Mashantucket Pequot tribe lived in what states?
The ancestors of the modern-day Mashantucket Pequot tribe, who were descended from the Pequot people, dominated the southern New England coastal areas, which included what is now Connecticut and Rhode Island.
So to evaluate the retrieval quality, I use the RAGAS framework. So traditional metrics such as BLEU and ROUCH mainly compare words overlap and grounded in retrieval context. RAGAS use an LM as judge to evaluate semantic quality instead of exactly words. So in this project, Gamma 431 billion cloud was used as the evaluator. So 5 metrics have an evaluate, which is faithfulness, answer relevancy, context precision and context recall, and the last answer correctness. For latency, I calculate the latency across 8 stages. So T1 is a stage people start speaking, Tn users stop speaking, T2 STT complete, T3 the RAG finish the retrieval, T4 the LM generation, and T5 is the time taken for TTS. So what we track? We track the time to first response. So time to first response is referred to the actual silence time after the users stop speaking. You have to be below 1.5 seconds. So lower TTFR improve the responsiveness and user experience. Next, I also evaluate the robustness against AR's noise. Why we evaluate AR's noise? Because in real voice-based applications, users queries first pass through STD systems. Then it will introduce transcription errors that will not appear in the text space. Testing with different WR levels allow us to measure how well the VectorRAG and GraphRAG maintain the retrieval and answer quality under realistic speech coordination conditions. So how we do that? We use WR rate by changing some of the words using substitution, deletion, and insertion into multiple WR rate. So because we use exactly the same WR error transcription test, so we allow a fair comparison of how well each architecture tolerates AR's errors. This I use 2 datasets with different characteristics. Squad dataset is mainly a factual single hop dataset where answers are usually found within 1 document, while Hopper QA is a multiple hop reasoning dataset where answers are distributed across multiple documents. Using both datasets allow us to evaluate both factual retrieval and reasoning capabilities. From the dataset of Squad dataset, VectorRAG show that it outperforms GraphRAG across all evaluation metrics. For example, the answer correctness increases for approximately 0.748 to 0.72, while faithfulness improved from 0.74 to 0.797. This indicates that VectorRAG is highly effective for factual single hop questions. So we find out that VectorRAG is performing better than the GraphRAG because of the direct intermapping with less noise generated. VectorRAG directly retrieves symmetrical similar chunks using embeddings, reducing unnecessary information, while GraphRAG may suffer from graph incompleteness and edge explosion, causing extra context to be retrieved. Therefore, VectorRAG achieves higher precision and factor accuracy. This is because when the GraphRAG uses the LM to extract the entity and relationships, the LM may misclassify the entity and also the relationships and causing the knowledge graph to be incompleteness, and hence it cannot retrieve the relationships cannot find out the nodes and cannot retrieve the relevant context. While for the noise, the GraphRAG, because the dataset is mainly factual and only contained into one document, so while doing the graph traversal, it is pulling a more unnecessary documents that not relevant to the most significant relevant to the questions generated. So it pull out more unnecessary information that can distract the LM. This is another dataset. Hotspot QA, you can see the GraphRAG, Excel, and multi-hop routing, it perform better than VectorRAG in this dataset. You can see the accuracy in the answer correctness is much higher than the VectorRAG. However, the GraphRAG is still vulnerable to graph incompleteness. We found that GraphRAG has the potential to outperform VectorRAG on reasoning dataset only when the knowledge graph will accurately capture the required entities and relationships. The GraphRAG is only as good as its graph. So we use the LM to extract all entities and relationships upfront when building the knowledge graph. So if it missing a granular details, the graph is permanently blind to it, and it cannot retrieve a relationship that was never mapped. And also, an edge explosion happens when theory highly connected nodes, it pulling in massive amount of irrelevant context that will drown out the answers and distract the decision of LM. However, the GraphRAG is still better than VectorRAG because it can bypassing VectorRAG semantic blindness. VectorRAG relies on semantic searching and keywords, while GraphRAG using graph traversals to seamlessly bridge scatter concept across multiple documents and gather the all needed information to help the LM to generate the answer. So instead of dumping raw unstructured barriers into the LM, GraphRAG fit in a clean map of relationships. These explicit maps act as a strict controls guiding LM to extract the right text with high faithfulness. Next, we evaluate the latency. The faster configuration of VectorRAG on squad dataset only take 3.67 seconds, which including the user start speaking time. And the GraphRAG have the slow configurations, which is take 11.03 seconds on the Hotspot QA. The overall input pace was take much longer time in Hotspot QA because the questions are mainly longer than the squad dataset. So from the observation, we can find out that the average RAG delay is the lowest is at the VectorRAG on squad dataset and the highest is GraphRAG on Hotspot dataset. While STD and LM and DTS are not the major contributors. It is because STD directly transcribes the words while users still speaking. The LM generates the first token directly passed to DTS, and DTS synthesizes it into audio without waiting LM to finish all sentences. So it does not including into the TTFR, which is the actual status field by the users. So the TTFR will basically based on the RAG have to wait STD to finish all the scripting speech and pass to it, and the RAG retrieve all relevant documents and pass to LM. So the most dominant in this guys agent is the RAG delay. So we can see that for both datasets, GraphRAG perform much more latency than VectorRAG. Only VectorRAG in squad dataset fulfill the threshold of good quality voice agent, which is between 1.5 thresholds. It because the retrieval differences, the GraphRAG use cross traversals which traverses across multiple documents, it introduces latency. While VectorRAG just simply compute the semantic similarities and retrieve the 5-chunk retrieval information. So in order to answer reasoning questions like why and when questions, the latency increases. Next, for the Romans again, ASR noise. VectorRAG also show better performance than GraphRAG in both Hotspot QA dataset and squad dataset. VectorRAG show a smaller performance drop than the GraphRAG as increases from 10 to 40% WEI levels. So why this happened? Because of the semantic similarities, it embeds the whole questions that retrieve a similar chunk. For example, what band than Jen's Bulgarian word with was originally called inferior breed. VectorRAG, the remaining words still provide semantic information that help to find the relevant context, while for GraphRAG, because it's missing the whole entities, it don't even find the nodes to perform graph traversal. So you can conclude that GraphRAG is a binary system only, and the VectorRAG is a continuous system. GraphRAG needs the exactly entity to find the relationships. So for the sustainability and impact, for societal impact, it optimizing this voice-based system, drastically improving accessibility. Fast, reliable, hand-free interface are crucial for elderly and visually impaired users. On the engineering side, this research defines the exactly architecture trade-offs between graph and vector retrieval, providing a clear roadmap of building a low-latency voice agent. Finally, regarding sustainability, lowering latency inherently reduces computational overheads. Highly efficient retrieval pipelines directly translate to reduced energy consumption SQ. So come up with a solution using routing skill, using VectorRAG in voice agent when users ask simple factual questions, and using GraphRAG on complex multi-reasoning questions. Next, the future work. Our main goal is to building a hybrid RAG architecture. We will use a theory classifier to automatically route simpler single-hop questions onto VectorRAG and complex multi-hop questions to GraphRAG. To improve accuracy, we must enhance the initial graph extraction process and use adaptive strategies to adjust retrieval size based on theory difficulty. Finally, we will extend the voice agent to support multilingual interactions across English, Malay, and Mandarin. So in conclusion, neither architecture is universal superior. VectorRAG performs better for factual questions, offer lower latency, and is more robust against ASR error, making it suitable for real-time voice agent. While GraphRAG excels in the multi-hop reason task by connecting information distributed across multiple documents. Therefore, the choice of architecture depends on application requirements and query types. Thank you.